Hello class. Today is basic substitution, which is a method for doing antiderivatives that reverse the chain rule. This slide here, we're going to practice doing a derivative that involves the chain rule, and then we're going to learn the integration techniques for reversing that process. If we were to go back to our derivative rules, and we're going to use this rule right here, the derivative of the sine of u, where u stands for some arbitrary function. Sine of u, if you do the derivative of it, you get the cosine of u, and then the chain rule says multiply this by u prime, which I'll put in the front. It's better putting that in the front than, if you put this over here, then sometimes people will accidentally do this calculation in their head first, which is incorrect. So to avoid that issue, it's better just to leave that u prime in front of the trig function. Another way of writing this is using Leibniz notation and doing this. The derivative with respect to x, so we're going to assume x is the independent variable, of the sine of u. And because this letter and this letter don't match, we have to make a general assumption that the u stands for some unknown function of x. And we would get the derivative of u, which in Leibniz notation is du dx, and then times the cosine of u. So this is communicating the same thing, just using Leibniz notation. So specifically, if I have the derivative of the sine of x, and I follow this rule, then the derivative will be the cosine of x, and then we put the derivative of x right here in the front. But the derivative of x with respect to x is just 1. So in the end, we really just get cosine of x, which is exactly what we knew from Calculus 1. Derivative of sine of x is cosine of x. What I'm trying to illustrate is the fact that this general rule works always. When the letters that are in this position and this position don't match, is when you need to have an expression like here, they don't match, x and u. Then you need to have this explicit expression here present, because we don't know what u is relative to x. So we need to have a du dx present. But when those two positions do match, like they do what you see currently in red, then there's going to be an implied 1 here. The derivative did happen, but it's a derivative of x with respect to x, which is just 1. So the letters could change on us. I could wipe out that letter and put a w there, but the x and the w don't match each other. So we would have to have the derivative of sine w would be cosine w, and then times a dw dx. We assume w is some function of x. If it's specified that that letter is a constant, then this part here will zero out and will make everything 0, which makes sense because if w is a constant, then sine of w is also a constant, and the derivative of a constant in the end is 0. So if I say, okay, well, what's the derivative of the sine of 3x? This time, the u position, it's given to us. It's an explicit function involving x. So we do say the derivative of this will be the cosine of that same argument, so we still have a 3x there. But then right here in front of this, we're going to multiply the cosine of x by the derivative of 3x, which is 3. And now let's go ahead and do our specific example. So the derivative of sine of, all that thing right there is just u. It's going to be the cosine of all that same stuff, right? For this part, you don't change the argument. And when I say argument, I'm referring to the 4x squared plus 1, the thing that we're doing the trig function of. But then right here in front, we multiply to the cosine the derivative of the argument. And the derivative of the argument using the power rule and the sum rule and the derivative of a constant rule is 8x plus 0. Or in other words, just 8x. Okay, so there's a little bit of review on using the chain rule and some of the notation involved. Now what we'd like to learn how to do is reverse this process. So if I were to give you this function here and say, hey, what's the antiderivative? We want to be able to reproduce this as the original function. Also, will I be able to do this if I make some changes? Like if I make this 8 be a 3 instead, what would be the antiderivative of this result? It won't be this. But we're going to learn how to do this no matter what number I put there, 8, 3, 7, whatever. In fact, here it is. I want to do an antiderivative. You see an indefinite integral here, right? We have an integral sign in the differential, and in between is called the integrand. And we're trying to find this indefinite integral notation means we're trying to find the general antiderivative of the integrand. But this is not an 8, it's a 3. So I don't expect to get simply this function here as an answer. It's going to be a multiple of that function. Now, the formal process for doing this is called doing a basic substitution. I recognize that I have some sort of function of another function, in this case cosine of something. This is called a composition. You have a function plugged into another function. So there's a composition at play, which is precisely when the chain rule gets used, when you differentiate compositions. But now we're trying to anti-differentiate, and I can see there's some sort of composition in play here. We're going to introduce a new variable. We're going to call the 4x squared plus 1 a new variable. So we'll say u, or any letter you want really, is equal to 4x squared plus 1. Now if that were the inside function and I knew a chain rule was involved, and I would need to know what the derivative of u was so I could see, what sort of coefficient I expect to see here in front. And so we're going to find the derivative of u, and I'm going to use Leibniz notation for this. So du dx is equal to 8x plus 0, so just 8x. Now from here there are two basic approaches for doing the next steps of a basic substitution. One approach is to solve this expression here for du and then construct the du. Let's do that first. So du is equal to, and I'm just going to multiply this dx right to the other side. So it's equal to 8x dx. And now I'm going to take my integral and try to construct this and replace it with du. I call this the constructing du approach. Notice in the original integrand we have the dx present and we have an x present, but we don't have an 8. We have a 3 there. So here's what I'm going to do. I'm going to regroup some things. I'm going to rewrite the integral. I'm going to leave the 3 where it's at. I'm going to do the cosine next, but I'm going to change the 4x squared plus 1 to a simple u. The x I'm going to group over here to this side with the dx. Next I want to continue to construct this expression. I want an 8 there. So I'm going to go ahead and just feel free to put in an 8, as long as I counter it with a 1/8. So if you look really at what's in red here, I really just multiplied x by 1, but in the form of 8 over 8. And I'm going to pull apart that 8 over 8. And since I can pull this all the way to the front of the integral because it's multiplication with a constant, we have 1/8 of 3 cosine u and then times 8x dx. Now I go through the actual substitutions. 8x dx is now present, and I can change that to simply du. And this 3, I'm also going to pull it out to the front to join the 1/8. So our line looks like this. We have 3/8 of cosine of u. I don't need the parentheses on that u. And then we have the du. When you do a substitution like this, our original integral was entirely in terms of x. But when I switch to a new variable, you must get the integral entirely in terms of u, including the differential. And in this particular case, notice that there are no more x's left. All the x's have been converted somehow to u's. So now we're faced with just a very simple integral, the integral of cosine of u du. This differential says to treat u like the independent variable. So we just have to say, what's the antiderivative cosine of u without worrying about any chain rule effects. And so antiderivative cosine is positive sign. And then we need the plus c. As soon as you do an actual antiderivative, don't forget the plus c, should enter your work. And then we do one final step, it's called the back substitution, where we change the u back into terms of x, which was 4x squared plus 1. And we arrive at an answer. I leave it to you to verify by differentiation and using the chain rule that this answer, when differentiated, will produce this integrand. A second approach is to take this derivative statement right here, and instead of solving it for du and then trying to construct the du like we just did, to solve it all the way for dx and only replace the dx. Let me show you what that looks like. So solve for dx. So we have one more step of dividing by the 8x to both sides. So dx is equal to du divided by 8x. Then we take the original problem, which is, right here. I'm going to just rewrite that. So we have an integral of 3x times the cosine, and then I will change the 4x squared plus 1 to a simple u, and then we have the dx. Okay, this time I didn't bother moving that x around because I'm not trying to construct the du. I'm just going to leave things where they are. I did change the thing that I'm calling u now, which is 4x squared plus 1. But now I'm going to do a change on the dx. I'm going to use this statement here to change the dx. All right, so this goes in right here for that dx position, and this integral winds up looking like 3x cosine of u. I'll leave the parentheses off that u this time. And the dx turns into du divided by 8x. Now I look for cancellation of the original variable. And notice, since this is multiplication here, I can peel this fraction apart and move this over here instead. And when I do that, the x's cancel, and the 3 over 8 becomes a constant that I can pull to the front of this integral, leaving only cosine of u and du, which is precisely, right, it matches, these are the same. They're just slightly two different routes of getting to this same destination. I'm not sure which of these approaches your teacher of Calculus 1 emphasized, but I did want to show you them both. Of course, we would then proceed like we did before. These two steps would be next and get the same answer. Okay, let's look at another one here. Maybe you want to pause this video and actually try to come up with the substitution you would do yourself. And then when you feel ready to see what I'm about to do, you can unpause it. Now, one clue in knowing what to call u, let me come back up to here. One clue in knowing what to call u is you look for something in this expression that if it were u, do you see the derivative of that u, or at least a multiple of that derivative, present as a factor? In other words, I know that the substitution will work because the derivative of 4x squared plus 1, its derivative is 8x. But what I see here as a factor is a multiple of 8x. 8x could be multiplied by a constant and turned into 3x. It's really not the coefficient that matters, it's the fact that the derivative of x squared involves x. And when you see that connection, then this x is likely here present because of a chain rule that happened. And when you see that chain rule connection here between two different pieces of this integrand, where a factor of the integrand is a derivative of another piece of the integrand, then you know that a substitution is a good way to reverse that chain rule. So when I look here, I do know that when I differentiate natural log of x, I'm going to get 1 over x. And this x that's down here, because it's in a denominator, it's like having a 1 over x out here instead. So I do see a connection between natural log of x and that x that's in a denominator. That's a clue that I should let u equal natural log of x. And you might as well include the plus 1, because when you differentiate, the plus 1 will go to 0. So if u is equal to natural log of x plus 1, then its derivative, du dx, I'll use Leibniz notation, is equal to just 1 over x. I'm going to go ahead and do the constructive approach. So I'm going to solve this only for du, so I just multiply this dx right to the other side, is equal to 1 over x dx. So now I'm going to rewrite the original integral. The thing I'm calling u, I'm going to change that to u, so this is just square root of u. The 5 and x down here and then the dx, right, this x here could be brought over to the side here as its own, fraction, as a 1 over x. So you could break apart your integral so it looks like this. This is just nice because then you see that this part here matches this, and so we can just change that to a du. So this winds up giving us the integral of the square root of u over 5, and then just simply du. So we have to have only u's now at this stage, no more x's. Let's see, the next thing I'm going to do to this is pull the denominator 5 out as a 1/5 in front of this integral and change that square root of u to a 1/2 power. And then we're going to apply the reverse power rule for u. So that we have the 1/5 out front. We have u. We're going to increase this power here by 1 exactly. So 1/2 plus 1 takes us to 3/2. And then we do a 1 over 3/2 in front of this, or you can just put its reciprocal, a 2/3 in front of that. And then don't forget the plus c. Whenever you do an antiderivative, a plus c should show up. In the same step, these disappear is the same step that the plus c shows up. As a final step here, I'm going to just combine those fractions in front to 2/15 and replace the u with what we said it was equal to, which is natural log of x plus 1. So we have a natural log of x plus 1, and that u was being raised to the 3/2. And that is done. Okay, let's look at the next one. Again, maybe you can pause the video and see what you could do with this on your own, and then unpause when you're ready. A good way to anti-differentiate tangent of x is to express it in terms of sines and cosines. And we know that the tangent is the same thing as the sine of x divided by the cosine of x. And this puts us in a position where we can do a substitution. If I were to call this u, its derivative is right down here in the denominator. Let's see if that works real fast. I'm going to let u be sine of x because I know the derivative of that du dx is cosine of x. And I'm going to solve for du. Du is equal to cosine of x times dx. But when I come up to here, and if I were to try to pull that cosine of x over to the side, it's going to be under a 1. So this is really a 1 over cosine of x times dx, not a cosine of x times dx. So I'm not able to construct the du like I would want, which suggests to us that maybe this substitution isn't helpful. I'm going to let this be u down here instead. Let the denominator be u. we know that the derivative of that denominator is negative sine of x dx. And this won't be a problem because the negative sine of x dx we can easily create. But we want a negative there, so I am going to insert a negative as long as I counter with a negative out here. So I just, negative times negative is positive, so I haven't really changed anything. But I'm now in a position where I can construct the du. So in my very next step, we have the negative that's in front, that stays, but the negative that's next to the sign, right, all of this part right here, it matches this. Oops, and I have I forgot to do something down here in my notes. I shouldn't put that there as that line because it's still here. So I should do a separate line that says this, du equals negative sine of x times dx. There we go. Now I have this matches that, which can be replaced with simply du. And you can put the du up here, up top, and then the bottom is, we're calling that u. Or you can write this way, negative integral 1 over u, and then the du off on the side. They're the same thing. But in either case, the antiderivative of 1 over u is the natural log of u. And we do have the negative in front. We need to keep that there. And then also, it's the absolute. Don't forget the absolute value bars. And then the plus c, because we did an antiderivative. And then the final step here is to back substitute. U is the cosine of x. And this is a good place to end. This is the correct antiderivative of tangent. And we're going to express it a slightly different way. If you recall a property of logarithms that says the following, if we have something like a number times a natural log, or any log for that matter, of b, that we can use a property of logarithms that brings that a up as an exponent on the b. I'm going to do that property by treating this negative 1 as a coefficient and bring it up. So it reads natural log of the cosine of x, and that's being raised to the minus 1 power. This is not to be interpreted as the inverse cosine, though. If I had written it this way, this is a different meaning. This is the arc cosine function, not the cosine of x, and then raised to the minus 1. And a number to the minus 1 power, the cosine of x to the minus 1 power means 1 over the cosine of x. 1 over the cosine of x is just the secant. So this is a second very common way to express the antiderivative of tangent. It doesn't involve any negatives, and so sometimes it's preferred, but they're both fine. This is a good time for you to, again, pause the video and try this one here, cotangent. It's going to be very similar to how we did tangent. You can try it on your own and then unpause the video and see if you agree with what I do here. Cotangent is cosine of x over sine of x. I'm going to let u be the denominator, not the numerator. And the derivative of u with respect to x is cosine of x. And then I'm going to skip a step by multiplying the dx already to that side. And there it is, cosine of x dx. No negatives needed in this case. That just turns into a du, and then the sine of x turns into a u. So we just wind up with this, whose antiderivative is natural log of absolute u plus c. And then the back substitution gives us natural log absolute, and u was sine of x. And this one is a little bit easier, no negative involved or using log properties to change your answer slightly. All right, this next one. Just because we're in a unit, which is on basic substitution, doesn't necessarily mean you're going to use basic substitution to do every integral. Part of what you should be learning is how to discern which method actually to use. This is something that you don't need a substitution to do. And so if you split the x up, whenever you have a single term in a denominator, you can do this and write your problem this way. And then simplify those, so that just becomes the integral of 1 plus 1 over x dx. Now I'm ready to integrate each of these term by term. So the antiderivative of 1 is x, and the antiderivative of 1 over x is natural log of x and absolute values, and then plus c. And really, just like that, we're done. It required just a little bit of prep work, and then we just anti-differentiated term by term, and we got an answer. But no substitution was required. Now this next one. Now don't do the following mistake. This is not allowed with fractions. You can't split a numerator over the pieces of a denominator. Now that will make sense if you try it with just numbers, something like this. In reality, this is 2/6, which is a third. But if I am tempted to split that 2 up, it would look like 2 over 2 plus 2 over 4. It would look like 1 plus a half, which is equal to 1 1/2, which is 3/2, right? They're not the same thing here. So be careful you don't do this. So we are going to try substitution. I'm going to again let u be the denominator. Letting u be an entire denominator is often a strategy that might be something to consider. Because if you can wind up with a 1 over u du, or some multiple of that, then those are easy antiderivatives. The derivative of du dx is equal to just 1. If I multiply the dx to the other side, then it just says that du and dx are interchangeable in this problem. So I'm going to come back up to here and rewrite this. So we have x over, the denominator is now u, and the dx I can change freely to du. Okay, so what happened in this case is the x's aren't gone. They didn't cancel or get used to create the du. And we cannot proceed, so don't do something like this. Don't say, okay, well, ignore the x and just do an antiderivative 1 over u du. Variables can't be factored out through an integral sign, only constants. So you have to be careful about that. Instead, we have to do what I call a twist. If there's still some x's left over in your integrand, we need to get them all into u's, and I can use this relationship here to accomplish that. Solve it for x. If u is equal to x plus 1, then x itself is equal to u minus 1. And then we can plug u minus 1 in for that x right there. And this will get us entirely into terms of u. Okay, so we've got an integral. The old variable is now completely converted into the new variable, and now we say, okay, can I anti-differentiate this? Well, what sets this apart from the original? I mean, at first glance, they look sort of similarly complicated, but in the latter case, or in this case right here, in the u case, the denominator is a single term, so I could split that u up. So we have u over u, which is minus a 1 over u, and then du. We're doing the integral of 1 minus 1 over u. And the antiderivative of 1 is, you think it, and then I'm going to say it. Some of you might have been thinking x, but that's only when the differential is dx. You have to use the differential to know how to antidifferentiate a constant. So the antiderivative of 1 with respect to u is u. And then the antiderivative of 1 over u is natural log of absolute u. And then plus c. And then we do our back substitution. The u is changed back to x plus 1 minus natural log of absolute of x plus 1, and then plus c. Now it's very common that if you're to look this one up in the back of a book or use an integral calculator to get it, that you're not going to see this plus 1 here. The reason that is because this is a free-floating constant, and it can be grouped with this free-floating plus c. Right? If c represents all numbers, then you can just absorb the plus 1 into that family of all possible numbers. And so you could just, to make your answer look a little more simple, just say x minus natural log of absolute x plus 1 plus all constants. This is the more common answer you're going to see if you look in the back of a book or use an integral calculator. That plus 1 will appear to have vanished for no reason, but it gets absorbed into the plus c. Okay, we just have one more slide. I just wanted to go over how to do a basic substitution when a definite integral is in play. I provided the graph of this function right here, and it's a graph that crosses the x-axis at the origin. Left of the origin, it's below the x-axis, and right of the origin, it's above the x-axis. And we're integrating from -1 to 4. So part of my area, this part here is negative, and part of my area up here is going to be positive. So I expect an interpretation of my final answer, whatever my final answer is going to be the green area minus the red area. So there's some cancellation of areas happening here because I'm integrating just over the entire interval from -1 to 4. I'm not breaking this up into pieces to find the two areas separately. All right, our purpose here is to show you how to do a definite integral when there's a substitution at play. Notice that there's an x squared plus 3. The derivative of x squared involves x. So I see a chain rule having occurred here. So I'm going to let u be that denominator, including the plus 3. The derivative of x squared plus 3 is 2x. The plus 3 goes away to 0. And solve this for du. If I stop here solving for du, then I'm going to do the constructive approach of du. Let's actually take this one step further and solve for dx. So now divide both sides by 2x, just to show you, again, the variety in which you can do this. Now it's important to note that these limits of integration, whenever you see limits on an integral, they always default to be numbers that represent the variable that's indicated by the differential. So they're x coordinates because the differential is a dx. You got to remember that 4 is an x coordinate and -1 is an x coordinate. So when I rewrite my integral from -1 to 4, but I do my change of variables, let's go ahead and do this. And there's an x up here I'm not changing, the bottom I'm changing to a u, and the dx I'm changing to 1 over 2x du. Now I see the x's cancel, and we have a 2 though down there still, so that comes out as a 1/2. And we have an integral from -1 to 4 of 1 over u du. This is tricky. Like if I were to give you this problem out of context, you would assume the limits of integration are in fact u coordinates, but they're not, they're x coordinates. So we have an issue here because notationally this is communicating something that's not correct. The way to get around this, and there's a few ways, you can ignore the limits of integration, or you can just write them there still, but remember that they're x coordinates. So when you get a final answer, you're going to have to do a back substitution to x's before you start plugging in those numbers. There's an alternative approach. At the very same step, where the differential is no longer dx, it's now du, it's appropriate to change the limits of integration to new numbers. And the key is this u equals x squared plus 3. All right, so I'm going to make a little table down here, x against u. The lower x coordinate was -1 and the upper was 4. Use this relationship to say, okay, if x is -1, what's u? Well, square -1, you get 1, and add 3, you get 4. If x is 4, what's u? Well, square x and get 16, and add 3, you get 19. So we do a change of limits as well. So the lower limit becomes 4, and the upper limit becomes 19, and now these match the differential, they're u coordinates. In general, the definite integral should have limits on it that match the differential. And the nice thing about this is that we have an integral I can finish in terms of u. I don't need to go back to x at all. So let's go ahead and take a few steps further. We get 1/2. The antiderivative is natural log absolute u. I don't need the plus c because this is a definite integral, but we need evaluation bar from 4 to 19. And then plug in 19 and 4, so we get 1/2 natural log of 19. The absolute values aren't needed because absolute value of 19 is just 19. And then minus 1/2 natural log 4. Right, I could simplify this a little bit further. If I wanted to, I could factor out a 1/2 and then use a log property that allows me to divide the two inputs, right? Because log of something minus log of something is log of input divided by input. That's one of our log properties we learn in algebra. And now I can use the log property that allows me to move that up as an exponent. So I could take this further and say this is a natural log of 19/4 to the 1/2. Right? 1/2 means you do a square root, so I could write this as natural log of the square root of 19/4. I can split up that radical to 19 and 4 separately, so that gives me a radical 19/2. And then I could reach for a calculator, and I get approximately 0.779. Now, what's the interpretation of this number given this picture? So this green has some sort of area. We'll say it has area 1, and the red has some amount of area. We'll say that's area 2. And the interpretation of this number right here, cancellation of areas happened. The geometric interpretation is that it's A1 minus A2. Right? Any area above minus any regions below, that difference in areas will be this number here, about 0.779. Okay, and that's how you do a definite integral where it required a substitution to get through it.